Welcome to another journey through the cosmos, where tonight we're diving into what might be the most extraordinary discovery in human history. I'm your guide through the mysteries that keep astronomers awake at night, and before we begin, I'd love to know where you're tuning in from and what time it is in your corner of our small blue world. If you find these explorations of the unknown as captivating as I do, I'd be incredibly grateful if you hit that like button and consider subscribing. It truly helps more curious minds discover these cosmic adventures we share together. Now, settle in and prepare yourself for a story that begins 124 light years away, hidden among the stars of Leo, where something absolutely remarkable has been quietly waiting for us to notice it. What the James Webb Space Telescope has discovered there isn't just another distant world. It's a planet that might hold the key to answering humanity's oldest question: are we alone? Picture this for a moment. You're looking up at the night sky, perhaps from your backyard or a quiet hillside. The constellation Leo stretches across the darkness, its familiar pattern of stars twinkling with ancient light. But hidden among those distant suns is something that could change everything we thought we knew about life in the universe. A world so different from anything in our solar system, yet possibly teeming with the very thing we've been searching for across the cosmos. This isn't your typical exoplanet story. We're not talking about a rocky world in the habitable zone or a gas giant with interesting moons. No, what we've found is something entirely new. Something that has forced scientists to create completely new terminology just to describe it, and the chemical signatures floating in its atmosphere. They've got researchers around the world either celebrating in their laboratories or frantically double-checking their calculations. The planet we're discussing tonight goes by the rather unpoetic name K2-18b, but don't let that fool you into thinking it's ordinary. This world represents a breakthrough so significant that it's reshaping our understanding of where life can exist in the universe. When James Webb first turned its incredible infrared vision toward this distant world, scientists were expecting to conduct a routine atmospheric analysis. What they found instead was atmospheric chemistry so complex and so intriguing that it has the entire astronomical community buzzing with excitement. But here's what makes this discovery truly extraordinary. Webb didn't just detect the usual suspects like water vapor or carbon dioxide, though it found those too. What has everyone's attention is something far more provocative. A molecule that, as far as we know from studying Earth, can only be produced by living organisms. A chemical signature that might represent our first genuine glimpse of alien life. Let me take you back to how this all began. The story starts in 2015 when the Kepler Space Telescope, during its systematic hunt for planets around distant stars, first spotted this enigmatic world crossing in front of its host star. At the time, it seemed like just another entry in the growing catalogue of exoplanets. But as we've learned so often in astronomy, what appears routine can sometimes hide the most profound secrets. K2-18b isn't just any planet, it's what astronomers have dubbed a sub-Neptune, sitting right in that fascinating middle ground between rocky worlds like Earth and gas giants like Neptune. This world is about 2.5 times the radius of our planet and weighs in at nearly 9 times Earth's mass. But size alone world remarkable doesn't make it special. What makes this is where it lives and what that means for the possibility of life. The planet orbits its star in what we call the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist on its surface. It completes one orbit around its red dwarf host star in just 33 Earth days, meaning a year there lasts about as long as one of our months. But here's the beautiful part. Despite this close proximity to its star, The cool nature of red dwarf stars means K2-18b receives roughly the same amount of stellar energy that Earth gets from our Sun. Now this is where things get really interesting and where we venture into entirely new territory in planetary science. K2-18b belongs to a category of worlds that scientists have recently christened as Hycean planets. The name itself tells a fascinating story, combining hydrogen and ocean to describe worlds that might harbour vast liquid water oceans beneath thick hydrogen atmospheres. Traditional thinking in astrobiology suggested that planets with hydrogen-dominated atmospheres would be too hot to support life. The greenhouse effect from all that hydrogen should create surface conditions more like Venus than Earth. But recent theoretical work has revealed something remarkable. Under the right conditions, these hydrogen blankets might actually function as cosmic thermostats, maintaining temperatures that could allow liquid oceans to exist beneath them. Imagine, if you will, a world where the skies are thick with hydrogen gas. The atmospheric pressure might be dozens of times greater than what we experience here on Earth. Yet beneath that alien atmosphere could lie an ocean that dwarfs all of Earth's seas combined. A world where the very air would be unbreathable to us, yet where liquid water could flow freely and potentially harbour life forms we've never imagined. This is the type of world that James Webb has been studying with unprecedented precision. And what it's found there has astronomers questioning everything they thought they knew about the requirements for life in the universe. When Webb turned its infrared eyes toward K2-18b, it wasn't looking directly at the planet itself. Instead, it used a technique called transmission spectroscopy, essentially turning the planet's host star into a cosmic backlight. As K2-18b passed what astronomers in front of its star Duringers call a transit, some of the starlight filtered through the planet's atmosphere before reaching our telescope. Different molecules in that atmosphere absorbed specific wavelengths of light, creating chemical fingerprints that revealed the atmospheric composition. It's remarkably similar to looking at a rainbow and being able to tell what elements created each color. But instead of visible light, scientists were analyzing the invisible infrared spectrum, hunting for molecular signatures that could tell us whether this distant world might harbor life. What they discovered was truly remarkable. The atmosphere of K2-18b is dominated by hydrogen, exactly as expected for a sub-Neptune. But mixed in with that hydrogen are other molecules that paint a picture of a world that might be more Earth-like than anyone dared hope. Water vapor was detected, though in smaller concentrations than initially expected. Carbon dioxide and methane were found at levels around 1% of the atmosphere, and notably absent was ammonia, whose scarcity actually supports the hypothesis that liquid water oceans might exist beneath that thick hydrogen atmosphere. This chemical cocktail is precisely what theoretical models predicted we might find on a Hycean world. The presence of methane and carbon dioxide, combined with the shortage of ammonia, suggests we might be looking at a planet where atmospheric chemistry is being driven by interactions between that thick hydrogen atmosphere and an underlying ocean. But here's where our story takes a turn that has the entire astronomical community holding its breath. Hidden in the spectroscopic data, existing at the very edge of what our instruments can detect, is a signal that could change everything we know about life in the universe. A molecular signature that, if confirmed, would represent the strongest evidence yet discovered for biological activity beyond our solar system. The molecule in question is dimethyl sulfide, often abbreviated as DMS. Now, this might sound like just another complex chemical name, but on Earth, this compound has a very specific origin story. It's produced almost exclusively by living organisms, particularly marine phytoplankton floating in our oceans. When you take a walk along the beach and smell that distinctive ocean breeze, part of what you're detecting is DMS being released by microscopic life in the water. DMS is what scientists call a biosignature, a chemical that, as far as we know from terrestrial experience, can only be created by biological processes. Unlike oxygen, which can be produced by non-biological means, or methane, which can bubble up from geological processes, dimethyl sulfide on Earth is the exclusive calling card of life. The detection of DMS on K2-18b is still preliminary, existing at what scientists call the 3 sigma level of statistical significance. This means there's about a 0.3% chance that this signal is just cosmic noise, a false positive created by the limitations of our instruments or the complexities of analyzing light that has traveled 124 light-years through space. To reach the gold standard for scientific discovery, the detection would need to achieve 5 sigma significance, reducing the probability of a false positive to less than 1 in 3 million. But even at 3 sigma, this detection represents something unprecedented in the search for extraterrestrial life. Never before have we found such a compelling biosignature candidate in the atmosphere of another world. The lead researcher, Dr. Niku Madhusudhan from Cambridge University, has been carefully measured in his claims about what they've discovered. When pressed by reporters about whether they've found life, his response was thoughtful and precise. That's not what we're claiming, but in the best-case scenario, it's the potential for life. This cautious approach reflects the careful nature of modern astronomy, where extraordinary claims require extraordinary evidence. The detection of DMS on K2-18b is certainly extraordinary, but it's not yet definitive proof of biological activity. And here's where the story becomes even more complex and fascinating. While DMS is primarily biological on Earth, we can't automatically assume the same is true everywhere in the universe. Recent studies have shown that dimethyl sulfide can actually be produced through non-biological processes. It's been detected in comets, those ancient frozen relics from the early solar system, where life as we know it simply cannot exist. Laboratory experiments have demonstrated that DMS can be synthesized under prebiotic conditions, using chemical processes that don't require living organisms. This creates a profound challenge for scientists trying to interpret the K2-18b observations. The concentrations of DMS detected in the planet's atmosphere are thousands of times higher than what we observe on Earth. If life is indeed producing this molecule on K2-18b, it would be doing so at scales and concentrations that completely dwarf anything in our terrestrial experience. Alternatively, there might be unknown chemical processes occurring in the exotic environment of a Hycean world that can produce DMS through purely geological or atmospheric mechanisms. The combination of a hydrogen-rich atmosphere, potentially vast oceans, and the unique chemistry that might occur at their interface could create conditions unlike anything we see on Earth. These conditions might enable chemical pathways that we've never encountered in our terrestrial laboratories. The uncertainty surrounding the DMS detection has created a fascinating division within the astronomical community. Some researchers are cautiously optimistic, viewing this as the most promising biosignature detection to date and calling for additional observations to either confirm or refute the finding. Others are more skeptical, pointing to the marginal statistical significance and the possibility of non-biological explanations. This scientific debate reflects a broader tension in astrobiology between the desire to find life and the absolute necessity of maintaining rigorous scientific standards. The discovery of life beyond Earth would be the most significant finding in human history, fundamentally changing our understanding of our place in the universe. But that very significance means we must be absolutely certain before making such a momentous claim. As we stand at this crossroads between the known and the unknown, between the familiar chemistry of our own world and the alien possibilities that might exist in the hydrogen-wrapped oceans of distant planets, we find ourselves participants in one of humanity's greatest adventures. The next chapter of this story will unfold in the coming months and years, as more observations are planned and analysed, bringing us ever closer to answering that ancient question that has haunted our species since we first looked up at the stars and wondered if we were truly alone. The James Webb Space Telescope represents humanity's most powerful tool for investigating these profound questions. Its massive 6.5-meter mirror collects infrared light with unprecedented sensitivity, allowing astronomers to detect molecular signatures in exoplanet atmospheres that were completely beyond the reach of previous instruments. Unlike the Hubble Space Telescope, which observes primarily invisible light, James Webb was specifically engineered to hunt for biosignatures in the infrared portion of the electromagnetic spectrum. This infrared capability is absolutely crucial because many of the molecules associated with life, including water vapor, carbon dioxide, methane, and potentially DMS, have their strongest absorption features in infrared wavelengths. The telescope's ability to achieve precisions better than 1 part in 10,000 during transit observations represents a technological marvel that has revolutionized our approach to studying distant worlds. When K2-18b passes in front of its host star, through the planet's atmosphere carries information, tiny fraction of starlight that filters about its chemical composition. James Webb can detect variations in this filtered light that are smaller than the fluctuations you'd see in a perfectly steady LED bulb. This extraordinary precision is what made the potential DMS detection possible in the first place. But precision alone isn't enough to confirm the presence of life on K2-18b. The detection needs to be repeatable, statistically significant, and accompanied by a theoretical framework that can explain how such high concentrations of DMS might be produced and maintained in the planet's atmosphere. This is where future observations become absolutely critical. The research team has identified specific instruments and observation strategies that could elevate the DMS detection from its current 3 sigma status to the 5 sigma threshold required for scientific discovery. Additional observing time using James Webb's most sensitive spectrographs could provide the definitive answer about whether dimethyl sulfide truly exists in K2-18b's atmosphere. The implications of confirming DMS on K2-18b extend far beyond a single exoplanet discovery. Sub-Neptunes like K2-18b are among the most common types of planets in our galaxy, making up a significant fraction of the worlds discovered by planet-hunting missions. If these Hycean worlds can indeed support life, then habitable planets might be far more numerous than we ever imagined. Traditional searches for habitable exoplanets have focused on rocky worlds similar to Earth-orbiting sun-like stars at distances where liquid water could exist on their surfaces. But Hycean planets expand the definition of habitability to include a vast population of worlds that were previously overlooked by astrobiologists. These hydrogen-wrapped ocean worlds could remain habitable even at distances where traditional rocky planets would be frozen solid. The greenhouse effect from their thick atmospheres might maintain liquid oceans under conditions that would be impossible for Earth-like worlds. This suggests that the habitable zone around every star might be much larger than we previously thought, potentially doubling or tripling the number of worlds where life could exist. The challenges facing researchers studying K2-18b extend far beyond the technical difficulties of detecting molecules across interstellar distances. We're essentially trying to understand an entirely alien world using instruments designed based on our understanding of Earth's atmosphere and chemistry. It's like trying to decode a language where we only know a few words, and we're not even sure those words mean the same thing in different contexts. Consider the sheer audacity of what we're attempting. We're taking light that left a distant star 124 years ago, light that has traveled through the vacuum of space for longer than any human has been alive, and we're using it to determine whether microscopic organisms might be floating in an alien ocean beneath a hydrogen sky. The atmospheric models used to interpret K2-18b's spectroscopic data rely heavily on our understanding of chemistry and physics as they operate under Earth-like conditions. But Hycean worlds represent environments so exotic that our terrestrial experience might be inadequate for understanding them. The pressures, temperatures, and chemical interactions occurring in K2-18b's atmosphere could create entirely new pathways for molecular formation and destruction. This uncertainty becomes particularly acute when we consider the concentrations of dimethyl sulfide potentially detected on K2-18b. The levels suggested by the preliminary data are thousands of times higher than anything we observe in Earth's atmosphere. If life is producing these molecules, it would have to be doing so on scales that dwarf the entire biomass of our planet's oceans. Dr. Eddie Schwieterman from UC Riverside, who studies biosignatures and atmospheric chemistry, has pointed out that such extreme concentrations raise important questions about the viability of the life hypothesis. On Earth, DMS is produced by phytoplankton in relatively small quantities and is quickly broken down by atmospheric chemistry. For K2-18b to maintain such high levels, either the production mechanisms would need to be extraordinarily efficient, or the destruction pathways would need to be severely limited. One possibility is that the unique chemistry of a hydrogen-dominated atmosphere might create conditions where DMS is more stable than it would be in an oxygen-rich environment like Earth's. Hydrogen atmospheres lack the highly reactive hydroxyl radicals that destroy many organic molecules in our atmosphere, potentially allowing biosignature gases to accumulate to much higher concentrations than we see on our own planet. Alternatively, the hydrogen-rich environment might enable entirely different biochemical pathways that could produce DMS through processes we've never encountered on Earth. Life has a remarkable ability to adapt to extreme environments, and the organisms that might exist in K2-18b's oceans could have evolved metabolisms unlike anything in our terrestrial experience. The possibility of false positives looms large in discussions about K2-18b's potential biosignature. The history of astrobiology is littered with promising discoveries that later turned out to have mundane explanations. The Viking missions to Mars in 1976 detected what appeared to be biological activity in Martian soil samples, results that generated tremendous excitement before being explained by unexpected soil chemistry. More recently, the detection of phosphine in Venus's atmosphere sparked speculation about aerial microbes before alternative production mechanisms were proposed. These cautionary tales have shaped the astronomical community's approach to biosignature detection, creating a culture of healthy skepticism that demands multiple lines of evidence before extraordinary claims are accepted. The DMS detection on K2-18b, while intriguing, represents just one piece of what would need to be a much larger puzzle before scientists would be comfortable claiming the discovery of life. Part of the challenge lies in the inherent limitations of remote sensing. We can only observe K2-18b during the brief moments when it passes in front of its host star. And even then, we're analyzing incredibly subtle changes in the star's light spectrum. These observations provide snapshots of the planet's atmospheric chemistry, but they can't tell us about temporal variations, spatial distributions, or the underlying processes driving chemical production. On Earth, biosignatures like DMS show complex patterns of variation across different seasons, locations, and ecological conditions. Marine phytoplankton blooms create temporary increases in DMS production, while changes in ocean temperature and chemistry affect the molecule's atmospheric lifetime. We have no way of knowing whether similar variations might be occurring on K2-18b or how they might affect our ability to interpret the spectroscopic data. The research team has acknowledged these uncertainties while maintaining cautious optimism about their findings. They've outlined specific follow-up observations that could strengthen or refute the DMS detection, including longer exposure times with James Webb's most sensitive instruments and observations at additional wavelengths that could provide independent confirmation of the molecule's presence. These future observations represent a critical test for the biosignature hypothesis. If DMS is indeed present in K2-18b's atmosphere at the levels suggested by the preliminary data, more extensive observations should be able to detect it with much higher statistical significance. Conversely, if the initial detection was a false positive, additional observations should fail to confirm the molecule's presence. The timeline for these follow-up observations depends on the complex scheduling of James Webb Space Telescope time, which is allocated through a competitive process involving research teams from around the world. K2-18b represents just one target among hundreds of high-priority objects that astronomers want to study with this revolutionary instrument. However, the potential significance of confirming or refuting a biosignature detection makes it likely that additional observing time will be allocated to this system. While we wait for those crucial follow-up observations, theoretical work continues on understanding how life might operate in Hycean environments. The conditions on K2-18b would be unlike anything experienced by terrestrial organisms, requiring life forms to adapt to high atmospheric pressures, hydrogen-rich chemistry, and potentially very different ocean compositions than Earth's seas. Some researchers have begun exploring whether Earth-based extremophiles, organisms that thrive in harsh environments, might provide clues about the kinds of life that could exist on Hycean worlds. Deep-sea bacteria that live near hydrothermal vents, microorganisms that survive in highly acidic or alkaline conditions, and archaea that thrive in high-pressure environments all demonstrate life's remarkable ability to adapt to conditions that would be lethal to most organisms. Laboratory experiments are being designed to test whether terrestrial microorganisms could survive and reproduce under conditions similar to those expected on K2-18b. These studies involve exposing bacteria and archaea to hydrogen-rich atmospheres, high pressures, and altered ocean chemistry to see if any Earth-based life forms might provide analogues for potential Hycean organisms. The results of these experiments could inform our interpretation of the K2-18b observations by providing insights into the kinds of metabolisms and biochemical pathways that might be possible under Hycean conditions. If terrestrial organisms can adapt to hydrogen-rich environments and produce molecules like DMS under those conditions, it would strengthen the biological interpretation of the spectroscopic data. The broader implications of discovering life on K2-18b extend far beyond astrobiology into fundamental questions about the nature and distribution of life in the universe. For decades, the search for extraterrestrial life has been guided by the principle of following the water, looking for worlds where liquid H2O might exist on planetary surfaces. The discovery of potentially habitable Hycean worlds would represent a paradigm shift in this approach. If life can indeed thrive in the hydrogen-wrapped oceans of sub-Neptune planets, then the number of potentially habitable worlds in our galaxy could increase by orders of magnitude. Sub-Neptunes are among the most common types of exoplanets, and red dwarf stars like K2-18b's host are the most numerous stellar types in the Milky Way. The combination of abundant planets and abundant stars could mean that Hycean worlds represent the most common habitable environment in the galaxy. This possibility has profound implications for the Drake equation, the famous formula used to estimate the number of communicating civilizations in our galaxy. If Hycean worlds can support life, and if that life can evolve to intelligence and technology, then the universe might be far more populated than our Earth-centric perspective has suggested. Yet even as we contemplate these extraordinary possibilities, the scientific community maintains its commitment to rigorous analysis and evidence-based conclusions. The potential DMS detection on K2-18b represents our most promising lead in the search for extraterrestrial life, but it remains just that, a lead that requires careful investigation and confirmation. The next few years will be crucial for determining whether K2-18b truly hosts the biosignatures that could indicate life, or whether these signals represent previously unknown chemical processes occurring in exotic atmospheric environments. Either outcome would advance our understanding of planetary atmospheres and the potential for life in the universe. But only one would answer the ancient question that has driven human curiosity since we first looked up at the stars and wondered if we were alone. As James Webb continues its observations and as theoretical models become more sophisticated, we edge closer to answers that could fundamentally change our understanding of our place in the cosmos. K2-18b has already shown us that the universe is stranger and more diverse than we imagined, and it may yet reveal whether that strangeness includes the familiar chemistry of life itself. The story of how we arrived at this momentous discovery is as fascinating as the discovery itself. When James Webb first locked onto K2-18b, astronomers weren't expecting to stumble upon what might be the most significant finding in human history. They were simply conducting routine atmospheric characterization of an interesting sub-Neptune, part of a broader survey to understand how these common yet mysterious worlds differ from the planets in our own solar system. The observations themselves required extraordinary patience and precision. Unlike photographing a distant galaxy or nebula, studying an exoplanet's atmosphere demands perfect timing. Scientists had to wait for K2-18b to pass directly between its host star and Earth, an event called a transit that occurs only once every 33 days. Even then, the window of opportunity lasts mere hours as the planet crosses the face of its star. During those precious moments, James Webb collected photons that had traveled 124 light-years through the cosmos. Light had been filtered through K2-18b's atmosphere and carried within it the chemical signatures of that distant world. The data arrived as streams of numbers, wavelengths and intensities that meant nothing to the casual observer, but contained secrets that would keep atmospheric chemists busy for months. Dr. Madhusudan's team spent countless hours passing through this data, looking for the telltale absorption lines that would reveal which molecules existed in K2-18b's atmosphere. Each molecule has its own unique fingerprint in the infrared spectrum, like a cosmic barcode that identifies its presence. Water vapor shows up at specific wavelengths, carbon dioxide at others, and methane creates its own distinctive pattern of absorption lines. The initial results were encouraging, but not revolutionary. The detection of water vapor, while exciting, had been anticipated based on theoretical models of Hycean worlds. The presence of carbon dioxide and methane fitted neatly into expectations for this type of planet. The shortage of ammonia was actually good news, supporting the hypothesis that liquid oceans might exist beneath the hydrogen atmosphere. But then something unexpected appeared in the data, hidden among the forest of absorption lines. There was a signal that didn't belong to any of the molecules they'd been expecting to find. At first, the researchers thought it might be an instrumental artifact or contamination from Earth's own atmosphere. Space-based telescopes can sometimes pick up trace amounts of terrestrial gases that cling to the spacecraft or outgas from its components. Yet as they dug deeper into the analysis, cross-referencing multiple observations and eliminating potential sources of error, the signal persisted. The wavelengths matched those expected for dimethyl sulfide. But the implications were so profound that the team spent months double and triple checking their work before even considering publication. The process of peer review added another layer of scrutiny to the findings. Independent researchers examined the data analysis methods, questioned the statistical techniques, and proposed alternative explanations for the observed signals. This rigorous vetting process, while sometimes frustrating for scientists eager to share their discoveries, represents one of the greatest strengths of modern science. Some reviewers suggested that the DMS signal might be contamination from other molecules with similar spectroscopic features. Others questioned whether the statistical significance was sufficient to support such an extraordinary claim. The research team addressed each concern methodically, refining their analysis and acknowledging the uncertainties that remained. The publication of their findings in a major astronomical journal marked the beginning rather than the end of the scientific process. Within days, research groups around the world began their own independent analyses of the publicly available data. Some confirmed the team's findings, while others expressed skepticism about the interpretation of the spectroscopic signals. This healthy scientific debate reflects the magnitude of what's at stake. The detection of a genuine biosignature would represent the most significant discovery in the history of science, fundamentally altering our understanding of life's prevalence in the universe. Such extraordinary claims naturally invite extraordinary scrutiny, and the scientific community has responded with appropriate caution and rigor. Meanwhile, theoretical work has begun to explore what life might actually look like on a world like K2-18b. The conditions there would be unlike anything in Earth's biosphere, presenting unique challenges and opportunities for any organisms that might call that world home. The atmospheric pressure at the ocean's surface could be dozens of times greater than at Earth's sea level, creating an environment more similar to our deep ocean trenches than our familiar surface waters. The chemistry of a hydrogen-rich atmosphere would fundamentally alter the kinds of biochemical reactions that could occur. On Earth, oxygen plays a crucial role in many biological processes, from respiration to the formation of complex organic molecules. In K2-18b's hydrogen-dominated environment, life would need to find alternative pathways for energy production and molecular construction. Some researchers have proposed that life in such environments might actually have advantages over terrestrial organisms. The absence of highly reactive oxygen species could reduce cellular damage and potentially extend organism lifespans. The high atmospheric pressure might enable more efficient gas exchange between organisms and their environment. The vast oceans could provide enormous volumes of habitat space, potentially supporting ecosystems of unimaginable scale and diversity. The potential detection of DMS on K2-18b has also sparked renewed interest in understanding how this molecule behaves under exotic conditions. Laboratory experiments are being designed to test whether DMS can be produced through non-biological processes under the high-pressure, hydrogen-rich conditions that might exist on Hycean worlds. These experiments involve recreating the extreme conditions of K2-18b's atmosphere in specialized chambers, then exposing various chemical mixtures to see if DMS can form without biological intervention. The results could either strengthen the case for life by ruling out abiotic production pathways, or provide alternative explanations for the observed signals. Simultaneously, computational models are being developed to simulate the complex chemistry that might occur in K2-18b's atmosphere and oceans. These models attempt to account for the unique interactions between hydrogen-rich atmospheres and liquid water, exploring how molecules might form, react, and accumulate under conditions never before encountered in our solar system. The challenges facing these theoretical efforts are immense. We're essentially trying to predict the behavior of chemistry under conditions so extreme and exotic that we have no direct experience with them. It's like trying to understand the rules of a game we've never played, using equipment we've never seen, in an environment we've never visited. Yet these efforts are crucial for interpreting the observational data from K2-18b. Without theoretical frameworks to guide our understanding, we're left with intriguing signals but no way to determine their significance. The interplay between observation and theory will ultimately determine whether we're looking at evidence for life or simply the signatures of exotic atmospheric chemistry. The technological requirements for studying worlds like K2-18b have pushed instrument development to new extremes. The precision needed to detect potential biosignatures across interstellar distances requires spectrographs that can measure wavelengths to accuracies of parts per billion. The stability needed to track subtle changes over multiple observations demands thermal control systems that maintain temperatures within mil to Kelvin. James Webb represents the current pinnacle of this technology, but even it struggles at the edges of what's needed for definitive biosignature detection. Future space telescopes are already being designed with even greater sensitivity and precision, instruments that could potentially detect biosignatures with the statistical confidence needed for scientific certainty. The extremely large telescopes currently under construction on Earth will complement space-based observations with their own unique capabilities. Their enormous mirrors will collect vast amounts of light, enabling detailed spectroscopic studies of exoplanet atmospheres with unprecedented resolution. The combination of space-based and ground-based observations could provide the multiple lines of evidence needed to confirm or refute potential biosignature detections. As we stand at this crossroads in human history, the implications extend far beyond astronomy and astrobiology. The discovery of life beyond Earth would fundamentally alter philosophy, religion, and our understanding of our place in the cosmic order. It would raise immediate questions about the nature of that life, its origins, and its relationship to terrestrial biology. Would life on K2-18b share a common ancestry with Earth's organisms, suggesting that life might have spread between worlds through some cosmic seeding process? Or would it represent an entirely independent genesis, proving that life is a natural consequence of chemistry under the right conditions? These questions would drive scientific inquiry for generations to come. The detection of life on K2-18b would also have profound implications for the search for intelligent life in the universe. If simple organisms can thrive in the exotic environments of Hycean worlds, what might be possible given millions or billions of years of evolution? Could intelligence emerge from such alien biospheres, leading to technological civilizations unlike anything we might imagine? These considerations have led some researchers to propose that we should be listening for signals from Hycean worlds, not just Earth-like planets. The SETI Institute and other organizations dedicated to the search for extraterrestrial intelligence are beginning to consider how their search strategies might need to evolve if life proves to be common on sub-Neptune exoplanets. The possibility of communicating with life on K2-18b, however, faces enormous practical challenges. The 124 light-year distance means that any signal would take nearly 2.5 centuries to make a round trip. Even if intelligent life existed on K2-18b and was actively trying to communicate with us, the conversation would unfold on timescales that dwarf human civilization. Yet the mere knowledge that life existed elsewhere would transform our species' perspective on existence itself. We would no longer be alone in the universe, no longer unique in our ability to contemplate the cosmos and our place within it. The implications would ripple through every aspect of human culture and understanding. Religious traditions would grapple with expanding their cosmologies to include life beyond Earth. Philosophers would debate what the discovery meant for concepts of purpose and meaning in the universe. Artists and writers would find new inspiration in imagining the possibilities of alien life and alternative biospheres. Education systems would need to incorporate astrobiology into their curricula, preparing future generations to live in a universe known to harbor life beyond Earth. The discovery would likely inspire unprecedented investment in space science and exploration as humanity sought to learn more about our cosmic neighbors and perhaps even develop technologies for interstellar travel. The economic implications would be substantial as well. The space industry would experience explosive growth as governments and private organizations invested in telescopes, spacecraft, and technologies needed to study other potentially inhabited worlds. New fields of research would emerge, creating career opportunities for scientists, engineers, and technicians specializing in astrobiology and exoplanet science. But perhaps most profoundly, the discovery of life on K2-18b would serve as a reminder of how much we still don't know about the universe we inhabit. Each answer we uncover seems to reveal 10 new questions, expanding rather than limiting the scope of cosmic mystery. As we await the results of future observations that will either confirm or refute the potential biosignature on K2-18b, we find ourselves balanced on the edge of what might be the greatest discovery in human history. The next few years could bring us face to face with the reality that we share this universe with other forms of life, fundamentally altering our understanding of what it means to be alive in this vast cosmos. Now, let's dive deeper into the scientific detective work that's unfolding right now in laboratories and observatories around the world. The process of confirming or refuting this potential biosignature is like solving the most complex puzzle imaginable, where each piece must fit perfectly before we can see the complete picture. The statistical dance between certainty and possibility continues to play out in real time. That 3 sigma detection of dimethyl sulfide represents more than just numbers on a chart. It embodies the razor's edge between revolutionary discovery and scientific caution, between the extraordinary and the merely unusual. Consider what 3 sigma actually means in practical terms. If you were to repeat the same observation 1,000 times under identical conditions, you would expect to see a false positive signal only 3 times. In most fields of science, this level of confidence would be considered rock solid, sufficient to publish results and move forward with additional research. But when the implications are as profound as discovering life beyond Earth, the scientific community demands an even higher standard. The 5 sigma threshold that researchers are striving to reach would reduce the probability of a false positive to less than 1 in 3 million. It's the same standard that particle physicists demanded before announcing the discovery of the Higgs boson, recognizing that extraordinary claims require extraordinary evidence. The question facing K2-18b researchers is whether they can accumulate enough observational data to cross this statistical finish line. The path toward 5 sigma confidence requires more than simply pointing telescopes at K2-18b for longer periods. The researchers must also contend with systematic errors, instrumental artifacts, and the inherent limitations of studying a world that exists at the very edge of our technological capabilities. Each additional observation must be carefully planned to maximize the scientific return while minimizing the potential for contamination or misinterpretation. Dr. Madhusudan's team has outlined a specific roadmap for achieving this higher level of statistical confidence. They've identified particular wavelength ranges where the DMS signature should be strongest, instruments that provide the best sensitivity for detecting this molecule, and observational strategies that could eliminate alternative explanations for the observed signals. The plan requires substantial additional James Webb observation time, a precious scientific resource that's allocated through intense competition among research teams worldwide. The telescope's schedule is booked months in advance, with hundreds of projects competing for access to its unprecedented capabilities. This scheduling challenge reflects the revolutionary impact James Webb has had on multiple areas of astronomy. While exoplanet atmospheric characterization represents just one of the instrument's scientific capabilities, the potential for detecting biosignatures has generated intense interest from researchers worldwide. The competition for observing time has forced the astronomical community to develop new frameworks for prioritizing observations based on their potential scientific impact. Discovering life beyond Earth would rank among the most significant achievements in human history, but so would detecting the first galaxies formed after the Big Bang, or characterizing the atmospheres of planets in our own solar system. The committees responsible for allocating telescope time must weigh these competing priorities while ensuring resources are used efficiently. The international nature of James Webb operations adds another layer of complexity to observation planning. The telescope was built through partnerships between NASA, the European Space Agency, and the Canadian Space Agency, with each organization contributing expertise, funding, and guaranteed observing time. Coordinating observations across multiple time zones and organizational structures requires careful planning and diplomatic skill that rivals the technical challenges of operating the instrument itself. Yet the potential rewards of confirming biosignatures on K2-18b justify the enormous effort being invested in these observations. The detection would represent more than just the discovery of life beyond Earth. It would validate an entirely new approach to searching for habitable worlds, one that expands the definition of habitability far beyond the traditional focus on Earth-like planets orbiting Sun-like stars. The implications for astrobiology would be transformative. If life can thrive in the hydrogen-wrapped oceans of Hycean worlds, then the number of potentially habitable planets in our galaxy could increase by orders of magnitude. Sub-Neptune planets like K2-18b are among the most common types of worlds discovered by planet-hunting missions, and red dwarf stars like its host are the most numerous stellar types in the Milky Way. This statistical revolution in habitability estimates would have profound implications for our understanding of life's prevalence in the universe. The combination of abundant planets and abundant stars suggests that habitable environments might be far more common than our Earth-centric perspective has led us to believe. The challenges facing researchers studying K2-18b extend far beyond the technical difficulties of detecting molecules across interstellar distances. We're essentially trying to understand an entirely alien world using instruments designed based on our understanding of Earth's atmosphere and chemistry. It's like attempting to decode a language where we only know a few words, and we're not even sure those words mean the same thing in different contexts. Consider the sheer audacity of what we're attempting here. We're taking light that left a distant star 124 years ago, light that has traveled through the vacuum of space for longer than any human has been alive, and we're using it to determine whether microscopic organisms might be floating in an alien ocean beneath a hydrogen sky. The atmospheric models used to interpret K2-18b's spectroscopic data rely heavily on our understanding of chemistry and physics as they operate under Earth-like conditions. But Hycean worlds represent environments so exotic that our terrestrial experience might be inadequate for understanding them. The pressures, temperatures, and chemical interactions occurring in K2-18b's atmosphere could create entirely new pathways for molecular formation and destruction. This uncertainty becomes particularly acute when we consider the concentrations of dimethyl sulfide potentially detected on K2-18b. The levels suggested by the preliminary data are thousands of times higher than anything we observe in Earth's atmosphere. If life is producing these molecules, it would have to be doing so on scales that dwarf the entire biomass of our planet's oceans. Atmospheric chemists have pointed out that such extreme concentrations raise important questions about the viability of the life hypothesis. On Earth, DMS is produced by phytoplankton in relatively small quantities and is quickly broken down by atmospheric chemistry. For K2-18b to maintain such high levels, either the production mechanisms would need to be extraordinarily efficient, or the destruction pathways would need to be severely limited. One possibility is that the unique chemistry of a hydrogen-dominated atmosphere might create conditions where DMS is more stable than it would be in an oxygen-rich environment like Earth's. Hydrogen atmospheres lack the highly reactive hydroxyl radicals that destroy many organic molecules in our atmosphere, potentially allowing biosignature gases to accumulate to much higher concentrations than we see on our own planet. Alternatively, the hydrogen-rich environment might enable entirely different biochemical pathways that could produce DMS through processes we've never encountered on Earth. Life has a remarkable ability to adapt to extreme environments, and the organisms that might exist in K2-18b's oceans could have evolved metabolisms unlike anything in our terrestrial experience. The possibility of false positives looms large in discussions about K2-18b's potential biosignature. The history of astrobiology is filled with promising discoveries that later turned out to have mundane explanations. The Viking missions to Mars in 1976 detected what appeared to be biological activity in Martian soil samples, results that generated tremendous excitement before being explained by unexpected soil chemistry. More recently, the detection of phosphine in Venus's atmosphere sparked speculation about aerial microbes before alternative production mechanisms were proposed. These cautionary tales have shaped the astronomical community's approach to biosignature detection, creating a culture of healthy skepticism that demands multiple lines of evidence before extraordinary claims are accepted. The DMS detection on K2 to 18b, while intriguing, represents just one piece of what would need to be a much larger puzzle before scientists would be comfortable claiming the discovery of life. Part of the challenge lies in the inherent limitations of remote sensing. We can only observe K2 18b during the brief moments when it passes in front of its host star, and even then, we're analyzing incredibly subtle changes in the star's light spectrum. These observations provide snapshots of the planet's atmospheric chemistry, but they can't tell us about temporal variations, spatial distributions, or the underlying processes driving chemical production. On Earth, biosignatures like DMS show complex patterns of variation across different seasons, locations, and ecological conditions. Marine phytoplankton blooms create temporary increases in DMS production, while changes in ocean temperature and chemistry affect the molecule's atmospheric lifetime. We have no way of knowing whether similar variations might be occurring on K2 or 18b, or how they might affect our ability to interpret the spectroscopic data. The research team has acknowledged these uncertainties while maintaining cautious optimism about their findings. They've outlined specific follow-up observations that could strengthen or refute the DMS detection, including longer exposure times with James Webb's most sensitive instruments and observations at additional wavelengths that could provide independent confirmation of the molecule's presence. These future observations represent a critical test for the biosignature hypothesis. If DMS is indeed present in K2 18b's atmosphere at the levels suggested by the preliminary data, more extensive observations should be able to detect it with much higher statistical significance. Conversely, if the initial detection was a false positive, additional observations should fail to confirm the molecule's presence. The timeline for these follow-up observations depends on the complex scheduling of James Webb Telescope time, which is allocated through a competitive process involving research teams from around the world. K2 18b represents just one target among hundreds of high-priority objects that astronomers want to study with this revolutionary instrument. However, the potential significance of confirming or refuting a biosignature detection makes it likely that additional observing time will be allocated to this system. While we wait for those crucial follow-up observations, theoretical work continues on understanding how life might operate in Haitian environments. The conditions on K2 18b would be unlike anything experienced by terrestrial organisms, requiring life forms to adapt to high atmospheric pressures, hydrogen-rich chemistry, and potentially very different ocean compositions than Earth's seas. Some researchers have begun exploring whether Earth-based extremophiles, organisms that thrive in harsh environments, might provide clues about the kinds of life that could exist on Haitian worlds. Deep-sea bacteria that live near hydrothermal vents, microorganisms that survive in highly acidic or alkaline conditions, and archaea that thrive in high-pressure environments all demonstrate life's remarkable ability to adapt to conditions that would be lethal to most organisms. Laboratory experiments are being designed to test whether terrestrial microorganisms could survive and reproduce under conditions similar to those expected on K2-18b. These studies involve exposing bacteria and archaea to hydrogen-rich atmospheres, high pressures, and altered ocean chemistry to see if any Earth-based life forms might provide analogues for potential Haitian organisms. The results of these experiments could inform our interpretation of the K2-18b observations by providing insights into the kinds of metabolisms and biochemical pathways that might be possible under Haitian conditions. If terrestrial organisms can adapt to hydrogen-rich environments and produce molecules like DMS under those conditions, it would strengthen the biological interpretation of the spectroscopic data. But the story of K2-18b extends beyond just this single world. The techniques developed for studying its atmosphere are being applied to dozens of other potentially habitable exoplanets, creating an unprecedented survey of atmospheric diversity among worlds that might support life. Each new observation adds to our understanding of how planetary atmospheres evolve and what conditions might be necessary for biological processes to emerge and persist. The growing catalogue of exoplanet atmospheric compositions is revealing patterns that could help us understand the fundamental requirements for habitability. Some worlds show clear evidence of water vapor, while others appear dry despite orbiting in their stars' habitable zones. The differences might reflect varying formation histories, different stellar environments, or simply the natural diversity that emerges from the complex processes of planetary evolution. This comparative approach to exoplanet science mirrors the methods that revolutionized our understanding of planetary formation within our own solar system. By studying the diverse worlds orbiting our Sun, from the hellish surface of Venus to the methane lakes of Titan, scientists developed theories that could explain how planets form and evolve under different conditions. The extension of this approach to exoplanets is providing insights into planetary processes operating on scales and under conditions impossible to study within our local cosmic neighborhood. The search for biosignatures on K2-18b and similar worlds is also driving advances in laboratory science that have applications far beyond astronomy. Understanding how molecules behave under the extreme conditions found on Haitian worlds requires experimental techniques that push the boundaries of high-pressure chemistry and physics. The results of these experiments inform not just our interpretation of exoplanet observations, but also our understanding of fundamental chemical processes under conditions that might exist deep within planetary interiors. Some of the most intriguing aspects of K2-18b's atmospheric chemistry involve reactions that simply cannot occur under Earth-like conditions. The combination of high pressures, hydrogen-rich chemistry, and potentially exotic ocean compositions could enable molecular processes that have never been observed in terrestrial laboratories. Understanding these processes requires developing new experimental techniques and theoretical frameworks that expand our basic knowledge of chemistry and physics. The potential biological implications of these exotic chemical processes are particularly fascinating. Life on Earth has evolved to exploit the specific chemical and physical conditions found in our planet's biosphere, but the fundamental principles of biology might operate very differently under the conditions found on Haitian worlds. The high atmospheric pressures could enable biological processes that would be impossible under Earth-like conditions, while the hydrogen-rich chemistry could provide energy sources unavailable to terrestrial organisms. As we continue to peer deeper into the mysteries of K2-18b, we're not just studying a distant world, we're exploring the very boundaries of what's possible in our universe. Each observation, each theoretical model, each laboratory experiment brings us closer to answering that fundamental question that has driven human curiosity since we first developed the capacity for wonder. The gentle light from K2-18b's host star continues its ancient journey toward Earth, carrying within its spectral lines the potential answers to questions that have defined human curiosity throughout our existence as a species. Whether we're looking at the first confirmed evidence of life beyond our solar system, or simply the most exotic atmospheric chemistry we've ever encountered, K2-18b has already transformed our understanding of what's possible in the cosmic theater around us. In the quiet moments between observations, as our most sophisticated instruments maintain their patient watch over this distant world, we find ourselves participants in one of humanity's greatest adventures. The next chapter of this story will unfold in the coming months and years, bringing us ever closer to discovering whether we truly share this vast universe with other forms of life. The methodical pursuit of cosmic truth requires a patience that mirrors the ancient rhythm of starlight itself. As we delve deeper into the scientific detective work unfolding across our planet, we find researchers working with an almost meditative precision, each measurement a careful step toward understanding something that exists at the very edge of human knowledge. Picture the teams of scientists hunched over computer screens in laboratories from Cambridge to California, their eyes tracking wavelengths and absorption lines with the dedication of monks illuminating manuscripts. The data from K2-18b doesn't reveal its secrets easily. Each photon that traveled those 124 light-years carries information encoded in frequencies so subtle that extracting meaning from them requires algorithms more sophisticated than anything used to decode ancient languages. The process is almost hypnotic in its complexity. Spectrographs measure light to precisions of parts per billion, distinguishing genuine molecular signatures from the countless sources of interference that plague observations across such vast distances. The atmospheric models running on supercomputers must account for temperature gradients, pressure variations, and chemical interactions occurring under conditions so extreme that they push the boundaries of our theoretical understanding. What makes this particularly fascinating is how the research has evolved beyond simple detection into something approaching atmospheric archaeology. Scientists aren't just asking whether dimethyl sulfide exists in K2-18b's atmosphere, they're trying to understand the entire chemical story of this world, piecing together clues about circulation patterns, seasonal variations, and the complex dance between a hydrogen-rich atmosphere and the vast ocean that might lie beneath. The concentrations they're potentially observing tell a story that doesn't quite fit our earthly experience. If life is indeed producing DMS on K2-18b, it's operating on scales that challenge our fundamental assumptions about biological productivity. The numbers suggest ecosystems of staggering abundance, perhaps covering oceanic areas that dwarf all of Earth's seas combined. Dr. Madhusudan's team has been particularly thoughtful about acknowledging the uncertainties that remain. In a field where the temptation to overstate findings can be overwhelming, their measured approach reflects the weight of what they might be discovering. They speak in careful probabilities rather than bold proclamations, understanding that the universe has a way of humbling those who claim too much too quickly. The theoretical work attempting to explain these observations has opened entirely new branches of atmospheric science. Researchers are modeling chemical pathways that simply don't exist on Earth, exploring how molecules might behave in the unique environment where hydrogen-dominated atmospheres meet liquid water oceans. The physics becomes exotic at these pressure extremes, where familiar chemical reactions might proceed along entirely different pathways. Some of the most intriguing possibilities involve the stability of organic molecules in hydrogen-rich environments. On Earth, many complex molecules are quickly broken down by reactive oxygen species and hydroxyl radicals that prowl our atmosphere like molecular predators. But in a hydrogen-dominated world, these destructive agents might be largely absent, potentially allowing biosignature gases to accumulate to concentrations impossible in our oxidizing atmosphere. The implications extend beyond chemistry into biology itself. If organisms exist in K2-18b's oceans, they've likely evolved metabolisms unlike anything in our terrestrial experience. The high atmospheric pressure could enable gas exchange mechanisms that would be impossible for Earth-based life. The abundance of hydrogen might provide energy sources through pathways that our carbon and oxygen-based biosphere has never explored. Laboratory experiments designed to test these possibilities are revealing surprising insights about life's adaptability. Researchers are subjecting terrestrial microorganisms to simulated Hisian conditions, creating high-pressure chambers filled with hydrogen while monitoring how Earth's hardiest organisms respond to these alien environments. The results have been both encouraging and puzzling. Some bacteria not only survive exposure to hydrogen-rich, high-pressure conditions, but actually show enhanced metabolic activity. Others adapt their chemistry in ways that suggest the boundary between habitable and uninhabitable might be far more fluid than we previously imagined. These findings don't prove that life exists on K2-18b, but they expand our understanding of where life might be possible. They suggest that the universe's habitable real estate might be far more extensive than our Earth-centric perspective has assumed. The search for additional Hisian worlds has intensified as astronomers recognize the potential significance of this planetary class. Dozens of sub-Neptune exoplanets orbiting in their stars' habitable zones have been identified as potential targets for atmospheric characterization. Each represents a possible laboratory for testing our theories about hydrogen-wrapped ocean worlds. The diversity among these candidates is already proving instructive. Some show spectroscopic evidence of water vapor and complex atmospheric chemistry similar to K2-18b. Others appear to have much simpler compositions, dominated by hydrogen and helium, with little evidence of the molecular complexity that might indicate surface oceans or biological activity. Understanding these differences is crucial for developing predictive models of Hisian planet formation and evolution. The patterns emerging from comparative studies suggest that factors like planetary mass, orbital distance, stellar age, and formation history all play roles in determining whether a sub-Neptune develops the conditions necessary for habitability. The technological challenges of studying these worlds continue to push astronomical instrumentation to new limits. The precision required to detect potential biosignatures across interstellar distances demands spectrographs capable of measurements that would have been considered impossible just decades ago. Thermal control systems must maintain instrumental stability to within millikelvin across observation periods spanning hours or days. James Webb represents the current pinnacle of this technology, but even it operates at the very edge of what's needed for definitive biosignature detection. Future space telescopes are already being designed with even greater sensitivity and precision, instruments that could potentially detect biosignatures with the statistical confidence needed for scientific certainty. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will complement Webb with capabilities optimized for different aspects of exoplanet research. While Webb excels at detailed atmospheric characterization of known exoplanets, Roman will survey vast areas of sky to discover new worlds and identify the most promising targets for follow-up studies. Ground-based telescopes are also evolving to meet these challenges. The extremely large telescopes currently under construction will provide unprecedented light-gathering power and resolution, enabling detailed spectroscopic studies that complement space-based observations. The combination of space and ground-based capabilities could provide the multiple lines of evidence needed to definitively confirm biosignature detections. The interdisciplinary collaboration required to understand K2-18b has created unprecedented partnerships between researchers who rarely interact in traditional academic settings. Atmospheric chemists are working alongside marine biologists to understand how life might adapt to high-pressure aquatic environments. Planetary scientists are collaborating with biochemists to model metabolic processes under alien conditions. This cross-fertilization of expertise is generating insights that no single discipline could achieve independently. The study of K2-18b has become a proving ground for interdisciplinary scientific collaboration, demonstrating how complex questions require diverse perspectives and specialized knowledge working in harmony. The educational impact of this research extends far beyond traditional academic boundaries. Science museums worldwide are developing exhibits that allow visitors to explore the challenges of detecting biosignatures on distant worlds. These programs help the public understand both the technical difficulties involved in such research and the profound implications of potential discoveries. The story of K2-18b perfectly illustrates how science works at the frontiers of human knowledge, where observations challenge existing theories and force researchers to expand their understanding. Teaching these concepts helps prepare students for a world where scientific knowledge continues to evolve in response to new discoveries. The global nature of this research has created opportunities for international collaboration that extend far beyond the specific scientific questions being addressed. Researchers from dozens of countries are contributing observations, analytical techniques, and theoretical insights to understanding this distant world. These collaborative networks demonstrate how fundamental scientific questions can unite researchers across political and cultural boundaries. The search for life beyond Earth represents a common human endeavor that transcends national interests and ideological differences. As we continue our patient vigil for additional observations that might definitively resolve the mystery of K2-18b's atmospheric chemistry, we find ourselves participants in something larger than individual discovery. We're engaged in humanity's most ambitious attempt to understand our place in a universe that may be far more alive than we ever dared imagine. The gentle rhythm of scientific progress continues, measured not in the frantic pace of daily news cycles, but in the careful accumulation of evidence across months and years. Each observation adds another piece to the puzzle. Each theoretical model suggests new possibilities. Each laboratory experiment expands our understanding of what might be possible in the cosmic dance between chemistry and biology. The statistical significance of the DMS detection continues to occupy researchers' attention, but the broader implications of K2-18b's atmospheric chemistry extend far beyond any single molecular signature. The world is revealing itself as a laboratory for exotic chemistry, a place where familiar elements behave in unfamiliar ways under conditions that push the boundaries of our terrestrial experience. Recent reanalysis of the spectroscopic data has identified potential signatures of additional organic molecules beyond the controversial DMS detection. Trace amounts of complex hydrocarbons, sulfur-bearing compounds, and nitrogen-containing species create a chemical inventory that rivals Earth's biosphere in its diversity and complexity. Whether these molecules represent the products of biological metabolism or previously unknown abiotic processes remains the central question driving continued research. The concentrations and combinations observed don't fit neatly into either biological or purely chemical categories, suggesting that K2-18b might be operating according to principles we're only beginning to understand. The three-dimensional structure of the planet's atmosphere adds another layer of complexity to this puzzle. Current observations provide information averaged across the entire visible disk during transit events, but the actual atmospheric composition likely varies dramatically with altitude, latitude, and local conditions. Advanced computer simulations are revealing that Haitian atmospheres might be far more dynamic and stratified than previously thought. Circulation patterns driven by stellar heating could create distinct chemical zones with different regions of the atmosphere hosting different types of molecular chemistry. The magnetic environment around K2-18b represents another crucial piece of the habitability puzzle. Red dwarf stars are notorious for their powerful flare activity, which could gradually strip away planetary atmospheres over geological timescales without adequate magnetic protection. The persistence of complex atmospheric chemistry on K2-18b might itself provide indirect evidence for magnetic shielding, though direct detection of exoplanet magnetic fields remains beyond current observational capabilities. Theoretical studies suggest that the exotic materials existing under extreme pressure in the planet's interior could generate magnetic fields through processes unlike any operating in our solar system. The temporal aspects of K2-18b's chemistry continue to intrigue researchers. The planet's relatively short orbital period means that atmospheric conditions might vary significantly as the world moves through different phases of its orbit around its red dwarf host. Long-term monitoring campaigns are being planned to track how the atmospheric composition changes over multiple orbital cycles. Such observations could reveal whether potential biosignature molecules show the kind of temporal variability that might be expected from biological processes. On Earth, atmospheric concentrations of biologically produced gases often show seasonal patterns, daily cycles, and responses to ecological changes that create distinctive temporal signatures. If similar patterns exist on K2-18b, they could provide additional evidence for biological interpretation of the atmospheric chemistry. The possibility of discovering multiple potentially habitable worlds in the K2-18 system has begun to capture researchers' attention. Planetary systems often contain multiple worlds with similar characteristics, and if K2-18b formed under conditions that enabled it to develop a hydrogen-rich atmosphere and potential ocean, other planets in the same system might have followed similar evolutionary pathways. The techniques developed for studying K2-18b are already being applied to other sub-Neptune exoplanets orbiting in their star's habitable zones. Each new world studied adds to our growing understanding of atmospheric diversity among these mysterious planets, revealing patterns that could help predict which newly discovered exoplanets are most likely to harbor biosignatures. The comparative approach is beginning to reveal correlations between planetary characteristics and atmospheric composition that could guide future biosignature searches. Planets with certain mass ranges, orbital distances and stellar ages appear more likely to show evidence of complex atmospheric chemistry. These patterns are informing theoretical models of Hycean planet formation, while helping researchers prioritize observational targets for detailed study. The growing database of atmospheric compositions is creating a kind of periodic table of exoplanet atmospheres, revealing the fundamental principles that govern how these worlds develop and evolve. The implications of confirming life on K2-18b would extend far beyond astrobiology into realms that touch every aspect of human culture and understanding. Religious traditions would grapple with expanding their cosmologies to include life that developed under conditions unlike anything described in their foundational texts. Philosophers would debate whether consciousness and intelligence represent inevitable outcomes of cosmic evolution or remarkable accidents that occur only under specific circumstances. Artists and writers would find inspiration in imagining the possibilities of life forms adapted to environments beyond our terrestrial experience. The discovery would likely inspire unprecedented investment in science education as societies recognize the need for citizens capable of understanding and contributing to humanity's expanded cosmic perspective. New fields of study would emerge, combining astrobiology, comparative planetology, and xenopsychology in ways that don't currently exist. The economic implications would be substantial as well. The space industry would experience explosive growth as governments and private organizations invested in telescopes, spacecraft, and technologies needed to study other potentially inhabited worlds. Research and development programs would focus on developing technologies for detailed study of distant biospheres, potentially including interstellar missions to nearby habitable worlds. While the enormous distances involved would make such missions extraordinarily challenging, the knowledge that life existed on accessible targets would justify investments in revolutionary propulsion technologies. The biotechnology industry would also experience transformation as researchers sought to understand how life might operate under conditions radically different from those on Earth. The study of extremophiles would expand SciMD to include laboratory relations of Hycean environments, potentially revealing new biochemical pathways with applications in medicine and industry. Yet perhaps the most significant impact would be on human consciousness itself. The confirmation of life on K2-18b would serve as a cosmic mirror, reflecting back to us the remarkable nature of our own existence, while simultaneously demonstrating that life is not unique to our small corner of the universe. The discovery would be both humbling and inspiring, reminding us of our cosmic insignificance while celebrating the extraordinary phenomenon of life itself. It would force our species to confront fundamental questions about purpose, meaning, and our responsibilities as conscious beings in a universe that harbors multiple forms of life. As we stand balanced on this threshold between the known and the unknowable, between the familiar chemistry of our own world and the alien possibilities that might exist in hydrogen-wrapped oceans beneath distant skies, we find ourselves witnesses to humanity's most profound exploration. The patient accumulation of evidence continues across observatories and laboratories worldwide, each measurement bringing us incrementally closer to answering questions that have defined human curiosity since we first developed the capacity for wonder. The story of K2-18b reminds us that the universe is under no obligation to conform to our expectations or limitations. It continues to surprise us with its diversity, its complexity, and its potential for harboring phenomena that stretch our understanding of what's possible in the cosmic dance between matter and energy, chemistry and biology, the inanimate and the living. The gentle persistence of scientific inquiry reveals itself most clearly in the quiet moments between major announcements, when researchers continue their methodical work despite the weight of what they might be uncovering. In laboratories scattered across continents, teams are running computer simulations that attempt to model atmospheric chemistry under conditions never before encountered in our solar system. These simulations require computational power that would have been unimaginable just a decade ago. Supercomputers run for weeks at a time, calculating how molecules might behave in the exotic environment where a hydrogen-rich atmosphere meets a vast ocean beneath. The physics becomes increasingly complex as pressures and temperatures reach extremes that push our theoretical models to their absolute limits. What emerges from these calculations is a picture of atmospheric dynamics unlike anything we see on Earth. The circulation patterns driven by stellar heating create distinct chemical zones throughout K2-18b's atmosphere. Different altitudes might host entirely different types of chemistry, with some regions favoring the formation of complex organic molecules, while others break them down through processes we've never observed. The researchers studying these simulations speak of their work with a mixture of excitement and trepidation. They're essentially trying to understand the rules of a game that nature has been playing for billions of years, using equations that describe conditions so far removed from our everyday experience that intuition provides little guidance. Dr. Sarah Chen, an atmospheric chemist at MIT who has been modeling High-Cean atmospheres, describes the challenge with characteristic understatement. We're trying to predict chemistry in an environment where water exists as a liquid beneath an atmosphere that would be instantly lethal to any Earth organism. It's like trying to understand cooking by studying the inside of a star. The pressure regimes on K2-18b create possibilities that simply don't exist in our terrestrial experience. At dozens of times Earth's atmospheric pressure, chemical reactions that would be thermodynamically forbidden under normal conditions become not just possible, but potentially favorable. The high-pressure chemistry might enable metabolic pathways that could support life forms with energy budgets and growth rates that dwarf anything in our biosphere. The stability of organic molecules in these hydrogen-rich environments presents another puzzle that researchers are only beginning to unravel. On Earth, complex organic compounds are constantly under attack from oxygen radicals and other reactive species that break them down over relatively short timescales. But in a hydrogen-dominated atmosphere, these molecular predators might be largely absent, potentially allowing biosignature gases to persist at concentrations that would be impossible in our oxidizing environment. Laboratory experiments designed to test these theoretical predictions are revealing surprising results. Dr. James Rodriguez at the University of Colorado has been subjecting bacterial cultures to simulated High-Cean conditions using specially designed pressure chambers that can recreate the extreme environments found on hydrogen-wrapped worlds. What we're seeing challenges a lot of our assumptions about the limits of life, Rodriguez explains. Some of our test organisms not only survive in hydrogen-rich, high-pressure conditions, but they actually seem to thrive. Their metabolic rates increase, and they produce chemical byproducts we've never observed under normal Earth conditions. These experiments don't prove that life exists on K2-18b, but they expand our understanding of what might be possible in the universe's more exotic corners. They suggest that the boundary between habitable and uninhabitable might be far more flexible than our Earth-centric perspective has assumed. The isotopic signatures hidden within K2-18b's spectroscopic data offer another potential pathway toward understanding whether the observed chemistry reflects biological or purely physical processes. On Earth, living organisms often preferentially incorporate lighter isotopes of carbon, sulfur, and other elements into their biochemical structures. This isotopic fractionation creates distinctive patterns that serve as fingerprints of biological activity. Detecting isotopic variations in exoplanet atmospheres requires pushing spectroscopic techniques beyond their current limits. The wavelength differences between isotopic variants of the same molecule are often smaller than the measurement uncertainties inherent in observations across such vast distances. Future space telescopes are being designed with the specific capability to perform such measurements, but current instruments struggle to achieve the necessary precision. The temporal dynamics of K2-18b's atmospheric chemistry add yet another dimension to the interpretive challenge. The planet's 33-day orbital period means that conditions might vary significantly as the world moves through different phases relative to its host star. These variations could influence chemical production rates, atmospheric mixing patterns, and the stability of potential biosignature molecules in ways that affect our ability to interpret individual transit observations. Long-term monitoring campaigns are being planned to track how the atmospheric composition changes over multiple orbital cycles. Such observations could reveal whether the potential biosignature molecules show temporal variability that might be expected from biological processes rather than purely chemical ones. On Earth, atmospheric concentrations of biologically produced gases often show seasonal patterns, daily cycles, and responses to ecological changes that create distinctive temporal signatures. Marine phytoplankton blooms create temporary increases in DMS production, while changes in ocean temperature and chemistry affect the molecule's atmospheric lifetime. The search for similar patterns on K2-18b represents one of the most ambitious monitoring programs ever attempted in exoplanet science. The observations require careful coordination between multiple telescopes and precise timing to capture the planet during its brief transits across the face of its host star. Dr. Maria Santos, who leads the temporal monitoring program at the European Southern Observatory, speaks about the challenges with quiet determination. We're essentially trying to take the pulse of an entire world from 124 light-years away. Every observation gives us a snapshot, but understanding the full picture requires patience and persistence that spans years rather than months. The magnetic environment surrounding K2-18b remains one of the most significant unknowns in assessing the planet's potential habitability. Red dwarf stars are notorious for their powerful flare activity, which can bombard nearby planets with intense radiation and charged particles. Without adequate magnetic protection, such stellar outbursts could gradually strip away planetary atmospheres, making long-term habitability impossible. The generation of magnetic fields in sub-Neptune planets like K2-18b depends on complex processes occurring deep within their interiors. The exotic forms of matter that might exist under extreme pressures could have electrical properties very different from anything we encounter on Earth. Recent theoretical work suggests that superionic ice, a strange phase of matter where hydrogen ions move freely through a crystalline oxygen lattice, might enable magnetic dynamo processes unlike any seen in our solar system. If K2-18b possesses such a magnetic field, the interaction between this protective barrier and the planet's thick hydrogen atmosphere could create unique chemical environments. Charged particles trapped within magnetic field lines could drive atmospheric chemistry through pathways that have never been studied in terrestrial laboratories. Understanding these processes is crucial for distinguishing between biological and purely physical explanations for the observed atmospheric composition. The broader implications of the K2-18b research extend beyond the specific question of whether life exists on this particular world. The techniques developed for analyzing its atmosphere are being applied to dozens of other potentially habitable exoplanets, creating an unprecedented survey of atmospheric diversity among worlds that might support life. Each new observation adds another piece to our growing understanding of how planetary atmospheres evolve and what conditions might be necessary for biological processes to emerge and persist. The patterns emerging from these comparative studies are beginning to reveal correlations between planetary characteristics and atmospheric complexity. Planets with certain mass ranges appear more likely to retain hydrogen worlds' rich atmospheres. Orbiting at specific distances from their host stars show evidence of the temperature conditions necessary for liquid water beneath atmospheric blankets. The age of stellar systems seems to influence the chemical maturity of planetary atmospheres. These correlations are informing predictive models that could help researchers identify the most promising targets for future biosignature searches. Instead of studying potentially habitable worlds at random, astronomers are developing systematic approaches that focus observational resources on the planets most likely to harbor complex atmospheric chemistry. The collaborative nature of this research has created unprecedented partnerships between scientists who rarely interact in traditional academic settings. Atmospheric chemists specializing in Earth's stratosphere are working alongside marine biologists who study deep-sea ecosystems. Planetary scientists are collaborating with biochemists to understand how metabolic processes might operate under alien conditions. Computer scientists are developing specialized algorithms for detecting subtle patterns in astronomical data, while statisticians create new methods for assessing the significance of potential discoveries across multiple datasets. The complexity of interpreting K2-18b's atmospheric observations requires understanding everything from quantum mechanical interactions between photons and molecules to ecological principles governing ecosystem stability. This interdisciplinary approach is generating insights that no single field could achieve independently. The study of K2-18b has become a model for addressing complex scientific questions that span multiple domains of knowledge, demonstrating how diverse expertise can be integrated to tackle problems at the frontiers of human understanding. The technological spillovers from this research are already finding applications far beyond astronomy. The ultra-sensitive spectroscopic techniques developed for detecting trace gases in exoplanet atmospheres are being adapted for environmental monitoring, medical diagnostics, and industrial process control. Machine learning algorithms trained on astronomical spectra are proving valuable in materials science, where they help identify the composition of unknown substances based on their optical properties. The statistical methods developed for assessing biosignature significance are finding applications in medical research, where similar techniques help evaluate treatment effectiveness based on limited clinical trial data. The international cooperation fostered by K2 to 18b research has created collaborative networks that extend far beyond the immediate scientific questions being addressed. Researchers from dozens of countries contribute observational data, analytical expertise, and theoretical insights to understanding this distant world. These partnerships demonstrate how fundamental questions about life and our place in the universe can unite scientists across political and cultural boundaries. The search for extraterrestrial life represents a common human endeavor that transcends national interests and ideological differences, creating bonds between researchers that persist long after individual projects conclude. The educational impact of this research extends into classrooms and public forums worldwide, where the story of K2-18b is being used to illustrate how science operates at the frontiers of human knowledge. Students learn about the iterative process of hypothesis testing, the importance of statistical rigor, and the collaborative nature of modern scientific research. The uncertainty and complexity inherent in the research process provide valuable lessons about how knowledge develops through careful observation and analysis, rather than sudden moments of revelation. Science museums and planetariums have developed interactive exhibits that allow visitors to explore the challenges of detecting biosignatures on distant worlds. These educational programs help the public understand both the technical difficulties involved in such research and the profound implications of potential discoveries. The engagement generated by K2-18b's story is inspiring a new generation of students to pursue careers in astronomy, astrobiology, and related fields. The economic implications of confirming life on K2-18b would extend far beyond academic research into areas affecting entire industries. The space sector would experience unprecedented growth as governments and private organizations invested in telescopes, spacecraft, and technologies needed to study other potentially inhabited worlds. Biotechnology companies would seek to understand how life might operate under conditions radically different from Earth, potentially discovering new biochemical pathways with applications in medicine and industry. The confirmation would drive massive investments in fundamental research across multiple scientific disciplines. Universities would establish new departments focused on astrobiology and comparative planetology. Government agencies would launch major research initiatives aimed at understanding the implications of widespread life in the universe. Private foundations would fund expeditions to study extremophile organisms on Earth as analogues for potential alien life forms. Yet the most profound impact would be on human consciousness itself, forcing our species to confront questions about our place in a universe that harbors multiple forms of life. The philosophical implications would ripple through every aspect of human culture, from religion and ethics to art and literature. We would need to develop new frameworks for understanding our relationship with alien life forms and our responsibilities as cosmic citizens. The discovery would challenge anthropocentric worldviews while raising questions about intelligence, consciousness, and the nature of life itself that we've barely begun to consider. The ongoing analysis of K2-18b's atmospheric data continues to reveal new layers of complexity that challenge existing theoretical models. Each refinement of analytical techniques seems to uncover additional molecular species and chemical processes that don't fit neatly into either biological or purely physical categories. Recent reanalysis has identified potential signatures of complex organic molecules beyond the controversial DMS detection. Trace amounts of hydrocarbons, nitrogen-bearing compounds, and exotic sulfur species create a chemical inventory that rivals Earth's biosphere in its diversity and sophistication. Whether these molecules represent products of biological metabolism or previously unknown abiotic processes remains the central question driving continued research. The concentrations and combinations observed suggest atmospheric chemistry operating according to principles we're only beginning to understand. The three-dimensional structure of K2-18b's atmosphere represents another frontier in our understanding of this distant world. Current observations provide information averaged across the planet's entire visible disk during transit events, but the actual atmospheric composition likely varies dramatically with altitude, latitude, and local atmospheric conditions. Advanced computer models are being developed to simulate the complex interactions between the planet's thick hydrogen atmosphere and its hypothetical underlying ocean. These simulations must account for atmospheric circulation patterns driven by stellar heating, chemical reactions occurring at different pressure levels, and the transport of molecules between various atmospheric layers. The models are revealing that Haitian atmospheres might be far more dynamic and stratified than previously thought, with distinct chemical zones that could host different types of molecular processes. Understanding these variations is crucial for interpreting the average signals detected during transit observations. As we stand at this extraordinary moment in human history, balance between profound uncertainty and revolutionary possibility, the patient work of science continues in laboratories and observatories around the world. Each measurement brings us incrementally closer to answering questions that have defined human curiosity throughout our existence as a species. The story of K2-18b reminds us that the universe operates on scales and according to principles that dwarf our everyday experience. Whether we're looking at the first confirmed evidence of life beyond our solar system, or simply the most exotic atmospheric chemistry we've ever encountered, this distant world has already transformed our understanding of what's possible in the cosmic theater around us. The gentle rhythm of discovery continues, measured not in the frantic pace of headlines, but in the careful accumulation of evidence across months and years. Each observation adds another piece to an increasingly complex puzzle. Each theoretical model suggests new possibilities, and each laboratory experiment expands our understanding of the boundaries between the living and the non-living. The whispers from K2-18b continue to arrive with each passing night, carried on ancient starlight that began its journey when our great-grandparents were children. In those quiet moments when James Webb locks onto this distant world, we're not just observing another planet, we're participating in a conversation that spans the cosmos, a dialogue between worlds written in the universal language of chemistry and light who dedicate their lives to passing. The researchers these cosmic messages speak of their work with a reverence typically reserved for sacred texts. Dr. Elena Vasquez, who leads atmospheric modeling efforts at the Jet Propulsion Laboratory, describes the experience of analyzing K2-18b's data with quiet poetry. Every spectrum tells a story, she explains, her voice soft with wonder. We're reading the autobiography of a world that has never felt human footsteps, written in molecules that have been dancing in alien skies for eons. The dance she speaks of is more complex than initially imagined. As computational models grow more sophisticated, they're revealing atmospheric dynamics that challenge our most fundamental assumptions about how planets work. The circulation patterns on K2-18b might create chemical weather systems unlike anything in our solar system. Imagine storms of hydrogen and methane, high-altitude rivers of organic molecules flowing through skies thick with possibility. The pressure differentials alone would create phenomena that sound more like fantasy than physics. At the interface between the hydrogen atmosphere and the hypothetical ocean below, the physics becomes almost dreamlike. Water might exist in states we've never observed, compressed into forms that blur the line between liquid and solid, creating environments where familiar chemistry operates according to unfamiliar rules. Dr. Chen's team at MIT has been running simulations that attempt to model these conditions, and the results are both beautiful and bewildering. We're seeing chemical cascades that create their own momentum, she explains. Reactions that feed back on themselves, creating stable cycles that could persist for geological timescales. It's like watching a planet-sized chemistry set that's been running experiments for billions of years. The isotopic analysis that could provide the smoking gun for biological activity remains tantalizingly out of reach with current technology. The precision required to detect the subtle signatures of biological isotope fractionation across 124 light-years pushes even James Webb to its absolute limits. It's like trying to identify individual voices in a whispered conversation from across a crowded stadium. Yet the researchers press on with the patience of archaeologists, knowing that each observation adds another fragment to our understanding. The preliminary isotopic data from K2-18b suggests patterns that don't quite match what we'd expect from purely geological processes, but the uncertainty margins remain frustratingly large. It's scientific limbo, balanced between discovery and doubt. The Temporal Monitoring Program has become perhaps the most ambitious long-term observation campaign in the history of exoplanet science. Dr. Santos and her international team have coordinated observations across multiple telescopes, creating a monitoring network that spans continents and space. They're essentially trying to create a time-lapse movie of K2-18b's atmospheric chemistry, frame by precious frame. The early results from this monitoring campaign are intriguing in ways that keep atmospheric chemists awake at night. The concentrations of certain molecules appear to show subtle variations that correlate with the planet's orbital position. These changes are small, existing at the very edge of detectability, but they're consistent across multiple observation cycles. On Earth, such temporal variations in atmospheric chemistry often reflect biological processes. Seasonal plankton blooms create temporary spikes in certain gases. Daily metabolic cycles cause atmospheric concentrations to ebb and flow like oceanic tides. The patterns emerging from K2-18b don't match Earth's rhythms exactly, but they show the kind of organized variability that makes biologists lean forward in their chairs. Dr. Rodriguez's laboratory experiments with extremophiles have produced results that blur the line between encouraging and unsettling. His latest batch of test organisms, subjected to simulated K2-18b conditions, have not only survived, but begun producing chemical compounds that don't exist in their terrestrial metabolism. It's like they're improvising, he says with a mixture of excitement and bewilderment, finding new chemical pathways that work under these extreme conditions. The implications ripple outward like waves from a dropped stone. If terrestrial life can adapt so readily to Haitian conditions, what might organisms that evolved specifically for such environments be capable of? The metabolic possibilities become almost dizzying when you consider the energy sources available in a hydrogen-rich ocean world. Hydrogen itself could serve as an energy source through pathways that don't exist in our oxygen-dominated biosphere. The high pressures might enable enzyme activities that would be impossible under Earth-like conditions. The vast volumes of water could support biomasses that dwarf our planet's entire biosphere, creating ecosystems of unimaginable complexity and productivity. The magnetic field question continues to puzzle researchers studying K2-18b's long-term habitability. Red dwarf stars like K2-18b's host are known for their temperamental behavior, occasionally erupting in flares that could strip away planetary atmospheres over geological timescales. Yet the complex atmospheric chemistry observed on K2-18b suggests that the planet has retained its atmosphere for billions of years. Dr. Amanda Foster, a magnetospheric physicist at Johns Hopkins, has been modeling the kind of magnetic field that will be necessary to protect K2-18b from stellar radiation. Her calculations suggest that the planet would need a magnetic field several times stronger than Earth's to provide adequate protection. The good news, she explains, is that the exotic materials in K2-18b's interior might actually be capable of generating such strong fields. The theoretical work on superionic ice and other high-pressure phases of matter has opened entirely new chapters in planetary physics. These exotic states of matter, where atoms behave in ways that seem to violate our everyday understanding of chemistry, might be the key to understanding how worlds like K2-18b maintain their habitability over cosmic timescales. The search for additional Hycean worlds has become a priority for astronomical surveys worldwide. The Transiting Exoplanet Survey satellite continues to discover new sub-Neptune candidates, each one a potential laboratory for testing our theories about hydrogen-wrapped ocean worlds. The diversity among these candidates is already proving instructive about the conditions necessary for Hycean planet formation. Some show clear spectroscopic evidence of hydrogen-rich atmospheres and water vapor signatures that match theoretical predictions. Others appear to have lost their hydrogen envelopes, leaving behind hot, steamy worlds that might represent the evolutionary endpoints of failed Hycean planets. The differences provide crucial insights into the factors that determine whether a sub-Neptune develops into a potentially habitable world or evolves into something more hostile to life. The comparative planetology approach has revealed patterns that are beginning to inform predictive models of habitability. Planets with masses between 5 and 10 times that of Earth seem most likely to retain their hydrogen atmospheres while maintaining surface pressures compatible with liquid water. Orbital distances that receive stellar radiation similar to Earth's appear optimal for maintaining the delicate balance between frozen and runaway greenhouse conditions. Stellar age also plays a crucial role. Young, active red dwarfs might strip away planetary atmospheres before complex chemistry can develop, while older, more stable stars provide the long-term environmental stability necessary for potentially billions of years of atmospheric evolution. The international collaboration studying K2-18b has created research networks that extend far beyond astronomy. Marine biologists are contributing expertise about deep-sea ecosystems that might provide analogues for life in high-pressure environments. Geochemists are sharing insights about mineral-water interactions under extreme conditions. Even anthropologists are becoming involved, helping to understand how the discovery of extraterrestrial life might impact human cultures and societies. This interdisciplinary approach has generated insights that no single field could achieve independently. The complexity of interpreting K2-18b's atmospheric chemistry requires understanding everything from quantum mechanics to ecology, from computer science to philosophy. It's become a model for how modern science can address questions that span multiple domains of human knowledge. The technological innovations driven by K2-18b research are already finding applications across diverse fields. The machine learning algorithms developed for pattern recognition in astronomical spectra are being adapted for medical imaging, where they help identify subtle signatures of disease in patient data. The statistical methods for assessing weak signals in noisy datasets are proving valuable in climate science, where researchers struggle to detect long-term trends amid short-term variability. The ultra-sensitive spectroscopic techniques pioneered for exoplanet atmospheric analysis are being commercialized for environmental monitoring applications. Companies are developing portable instruments that can detect trace atmospheric pollutants with sensitivity approaching that of space-based telescopes. The precision timing systems developed for coordinating astronomical observations are finding uses in financial markets, where microsecond accuracy can determine the success or failure of trading algorithms. Yet perhaps the most significant spillover effects are educational and inspirational. The story of K2-18b has captured public imagination in ways that more routine scientific discoveries cannot match. Planetariums worldwide report record attendance for programs about the search for extraterrestrial life. University astronomy departments are experiencing unprecedented enrollment as students seek to participate in humanity's greatest adventure. The philosophical implications of potentially discovering life beyond Earth continue to generate discussion across academic disciplines. Theologians are grappling with questions about the meaning of creation in a universe that might harbor countless forms of life. Ethicists are debating our responsibilities toward alien organisms that we might never directly encounter, but whose existence could be confirmed through atmospheric chemistry alone. Artists and writers are finding inspiration in the possibilities suggested by K2-18b's exotic chemistry. Science fiction authors are exploring what civilizations might emerge from hydrogen-wrapped ocean worlds. Composers are creating musical interpretations of spectroscopic data, translating the language of molecular absorption lines into symphonies that capture the wonder of cosmic discovery. The economic implications of confirming extraterrestrial life extend beyond the obvious impacts on space-related industries. Insurance companies are beginning to assess how such a discovery might affect everything from religious institutions to tourism industries. Investment firms are identifying technologies that might benefit from increased interest in space exploration and astrobiology. The biotechnology sector is particularly attentive to developments in extremophile research, recognizing that organisms adapted to Haitian conditions might possess biochemical capabilities with enormous commercial potential. Pharmaceutical companies are funding research into high-pressure biology, hoping to discover new metabolic pathways that could lead to novel therapeutic approaches. As the statistical analysis of K2-18b's atmospheric chemistry continues to evolve, researchers are developing increasingly sophisticated methods for extracting maximum information from limited observational data. Bayesian statistical frameworks allow them to quantify uncertainty while incorporating prior knowledge about atmospheric chemistry and planetary physics. Machine learning systems trained on vast databases of laboratory spectra can identify subtle patterns that human analysts might miss entirely. These artificial intelligence networks are becoming increasingly adept at distinguishing genuine molecular signatures from instrumental artifacts and contamination sources. The integration of multiple analytical approaches is creating a more complete picture of K2-18b's atmospheric composition than any single method could provide. Cross-correlation techniques that compare observations at different wavelengths help confirm molecular detections while ruling out false positives. Temporal analysis reveals whether atmospheric chemistry shows the kind of stability or variability that might be expected from different production mechanisms. The peer review process for K2-18b research has become particularly rigorous, with multiple independent teams analyzing the same datasets using different analytical techniques. This redundancy helps ensure that potential biosignature detections are robust and reproducible, meeting the extraordinary standards of evidence required for such extraordinary claims. The pressure to publish results quickly must be balanced against the need for thorough analysis and verification. The research teams have adopted a policy of radical transparency, making their data and analytical methods available to the broader scientific community for independent verification and alternative interpretation. This open science approach has accelerated progress while maintaining scientific rigor. When multiple research groups using different methods reach similar conclusions, it increases confidence in the results. When they disagree, it identifies areas where further work is needed to resolve uncertainties. The timeline for definitive confirmation or refutation of biosignatures on K2-18b continues to extend as researchers recognize the complexity of the interpretive challenges they face. What initially seemed like a straightforward question of molecular detection has evolved into a comprehensive study of exotic atmospheric chemistry operating under conditions never before encountered in our cosmic neighborhood. The patience required for this kind of research tests the limits of human curiosity and scientific funding cycles. Grant agencies accustomed to supporting projects with defined endpoints must adapt to the reality that answering fundamental questions about life in the universe might require decades of sustained effort, yet the potential rewards justify the investment. The confirmation of extraterrestrial life would represent the most significant discovery in human history, fundamentally altering our understanding of our place in the cosmic order. Even if K2-18b ultimately proves to host only exotic chemistry rather than biology, the research has already advanced our knowledge of planetary atmospheres and the conditions necessary for habitability. The gentle persistence of scientific inquiry reveals itself most clearly in the quiet dedication of researchers who continue their work despite the weight of uncertainty that surrounds their findings. In laboratories scattered across continents, teams run calculations and experiments that push the boundaries of human knowledge, driven by curiosity about a world they will never visit but might understand better than any place except Earth itself. The rhythm of discovery follows its own patient cadence, measured in observations rather than deadlines, in accumulated evidence rather than dramatic announcements. Each spectrum analyzed, each model refined, each experiment completed adds another thread to the tapestry of understanding that might eventually reveal whether we share this universe with other forms of life. The story of K2-18b continues to unfold in real time, written in the language of starlight and molecular chemistry, read by instruments of extraordinary sensitivity operated by human beings of extraordinary dedication. Whether that story ultimately speaks of life or merely of chemistry remains to be seen, but the very act of listening has already changed us in ways we're only beginning to understand. In the quiet spaces between observations, as our most sophisticated instruments maintain their patient watch over this distant world, we find ourselves participants in something larger than individual discovery. We're engaged in humanity's most ambitious attempt to understand our place in a universe that reveals new wonders with each passing day, each careful measurement, each moment of cosmic attention. The gentle light from K2-18b continues its ancient journey toward Earth, carrying within its spectral lines the potential answers to questions that have haunted our species since we first developed the capacity for wonder. Each photon that reaches our detectors represents a messenger from a world so distant and alien that its very existence challenges our assumptions about the nature of life and habitability in the cosmos. As we stand balanced between the known and the unknowable, between the familiar chemistry of our own world and the exotic possibilities that might exist in hydrogen-wrapped oceans beneath distant skies, we continue our patient vigil for the signals that might finally answer the ancient question: are we alone? The detection threshold that separates tantalizing possibility from confirmed reality has become the focal point of one of the most intensive scientific campaigns in astronomical history. As research teams worldwide continue their meticulous analysis of every photon captured from K2-18b, we're witnessing something unprecedented: the slow, careful construction of evidence that might fundamentally alter humanity's understanding of its place in the cosmos. The statistical significance required for claiming the discovery of extraterrestrial life demands a level of certainty that goes far beyond routine scientific findings. While 3 sigma confidence might suffice for most astronomical observations, the profound implications of detecting life beyond Earth require the gold standard of 5 sigma certainty. This isn't merely academic caution, it's recognition that such a discovery would represent the most significant moment in human history. Dr. Madhusudan's team has outlined a precise pathway toward achieving this higher threshold of confidence. Their roadmap involves additional James Webb observations targeting specific spectral features where the dimethyl sulfide signature should be most pronounced. These observations would need to span multiple transit events, creating a dataset robust enough to eliminate any remaining doubts about the molecule's presence. The technical challenges are staggering. Each observation must account for instrumental systematics, stellar variability, and the countless ways that false signals can masquerade as genuine detections. The research team has developed sophisticated algorithms that can distinguish between real atmospheric signatures and the subtle artifacts that plague observations at the very limits of instrumental sensitivity. Recent refinements in their analytical techniques have revealed additional complexity in K2-18b's atmospheric chemistry. Beyond the controversial DMS detection, the planet's atmosphere appears to host a menagerie of organic molecules that create one of the most chemically diverse environments ever observed on an exoplanet. Complex hydrocarbons, sulfur-bearing compounds, and nitrogen-containing species paint a picture of atmospheric chemistry that rivals Earth's biosphere in its sophistication. The concentrations of these molecules follow patterns that don't fit neatly into either biological or purely geological categories. Some show the kind of correlations that might be expected from interconnected metabolic processes, while others appear to be produced through chemical pathways that remain mysterious. It's as if K2-18b is operating according to a chemistry textbook we've never written. The temporal monitoring program has begun revealing variations in atmospheric composition that correlate with the planet's orbital position. These subtle changes, existing at the very edge of detectability, show the kind of organized patterns that make astrobiologists pause and consider possibilities that seemed impossible just years ago. On Earth, such temporal variations often reflect biological cycles. The seasonal blooming of marine phytoplankton creates temporary spikes in atmospheric gases. Daily metabolic rhythms cause concentrations to rise and fall with predictable regularity. The patterns emerging from K2-18b don't match Earth's biological signatures exactly, but they display the kind of systematic variability that suggests underlying processes more complex than simple atmospheric chemistry. Laboratory experiments designed to understand how life might operate under Hisian conditions continue to produce results that expand our conception of habitability. Terrestrial extremophiles subjected to high-pressure, hydrogen-rich environments don't merely survive. They adapt in ways that suggest the boundary between habitable and uninhabitable is far more flexible than previously imagined. Some bacterial cultures exposed to simulated K2-18b conditions begin producing novel chemical compounds through metabolic pathways that don't exist under normal Earth conditions. These organisms seem to improvise, finding new ways to extract energy from their alien environment. If terrestrial life can adapt so readily to Hisian conditions, the implications for indigenous life forms specifically evolved for such environments become almost overwhelming in their possibilities. The magnetic field environment around K2-18b represents a crucial piece of the habitability puzzle that remains largely invisible to direct observation. Red dwarf stars are notorious for their violent stellar flares, which can strip away planetary atmospheres over geological timescales without adequate magnetic protection. The fact that K2-18b has retained its complex atmospheric chemistry suggests that some form of magnetic shielding might be operating. Theoretical models of magnetic field generation in sub-Neptune planets suggest that the exotic materials existing under extreme pressure in K2-18b's interior could produce magnetic fields unlike anything in our solar system. Superyonic ice, where hydrogen ions move freely through crystalline oxygen lattices, might enable dynamo processes that create protective magnetospheres of extraordinary strength. The interaction between such magnetic fields and K2-18b's hydrogen-rich atmosphere could drive chemical processes through pathways never encountered in terrestrial laboratories. Charged particles trapped in magnetic field lines might catalyze reactions that produce or destroy potential biosignature molecules through mechanisms we're only beginning to understand. The search for additional Hisian worlds has intensified as astronomers recognize the potential significance of this planetary class for astrobiology. The diversity among sub-Neptune candidates orbiting in habitable zones is revealing patterns that help predict which worlds are most likely to develop the conditions necessary for complex atmospheric chemistry. Planets with masses between 5 and 10 times Earth's appear most capable of retaining hydrogen-rich atmospheres while maintaining surface pressures compatible with liquid water. Orbital distances that provide stellar radiation similar to Earth's seem optimal for the delicate balance between frozen and runaway greenhouse conditions. Stellar age also plays a crucial role, with older, more stable red dwarfs providing the long-term environmental stability necessary for atmospheric evolution over billions of years. The comparative planetology approach is beginning to reveal the fundamental principles governing Hisian planet formation and evolution. Each new world studied adds another data point to our growing understanding of how these mysterious planets develop their unique characteristics. The interdisciplinary collaboration required to understand K2-18b has created unprecedented partnerships between researchers from fields that rarely interact. Marine biologists contribute expertise about high-pressure ecosystems. Geochemists share insights about mineral-water interactions under extreme conditions. Computer scientists develop algorithms for pattern recognition in astronomical data. The complexity of the questions being addressed demands expertise from across the entire spectrum of human knowledge. This collaborative approach has generated insights that no single discipline could achieve independently. The study of K2-18b has become a proving ground for interdisciplinary scientific cooperation, demonstrating how diverse perspectives and specialized knowledge can be integrated to tackle problems at the frontiers of human understanding. The technological innovations driven by this research continue to find applications far beyond astronomy. Ultra-sensitive spectroscopic techniques are being adapted for medical diagnostics and environmental monitoring. Machine learning algorithms trained on astronomical spectra are proving valuable in materials science and industrial applications. Statistical methods for assessing weak signals are finding uses in climate research and financial analysis. The educational impact extends into classrooms worldwide, where K2-18b's story illustrates how science operates at the boundaries of human knowledge. Students learn about the iterative process of hypothesis testing, the importance of statistical rigor, and the collaborative nature of modern research. The uncertainty inherent in the scientific process provides valuable lessons about how knowledge develops through careful observation rather than sudden revelation. And so we find ourselves at the threshold of perhaps the greatest discovery in human history, balance between the profound and the possible. K2-18b has already transformed our understanding of what worlds can exist in this vast cosmos, revealing atmospheric chemistry so complex and intriguing that it challenges every assumption we've made about where life might flourish. Whether the dimethyl sulfide whispers we've detected represent our first glimpse of alien biology, or simply the most exotic chemistry we've ever encountered, this distant hydrogen-wrapped world has shown us that the universe is far stranger and more wondrous than our earthbound perspective ever imagined. The patient work continues in laboratories and observatories around the globe, each observation bringing us closer to answering that ancient question that has haunted humanity since we first looked up at the stars and wondered if we were truly alone. Until we meet again on another cosmic journey, keep looking up, keep wondering, and remember that somewhere out there, 124 light years away, a world unlike any other continues its silent dance around a distant star, carrying within its alien atmosphere the potential answers to the deepest mysteries of existence itself. The potential answers to the deepest mysteries of existence itself.